Shall I start? Okay. So, good afternoon, everyone. I welcome you to the Monsoon Cafe presentation of this week. So, my name is Shikhar. I work under Professor Indam Chakrabarti. And today I'll be talking about, as the title suggests, decadal climate, some crucial aspects and its role in the current 2024 Lino Southern Oscillation transition. So, as the title suggests, my whole presentation is divided into two broad parts. In the first part, I will be talking about some literature which addresses the theory which is related to this decadal climate variability. And in the second part, I'll be talking about how decadal climate can also have an influence on higher frequency processes such as El Nino Southern Oscillation. So basically brief, like why it is important to understand the decadal climate. So first of all, this can be understood by this schematic, which we have seen many times. So this is global mean surface temperature anomalies from 1880 to 2020. So in recent decades, we have seen there's a sharp increasing trend in the global surface temperature, which is largely driven by the increase in the greenhouse gases in our atmosphere. But is this trend entirely driven by the greenhouse gases? The answer is no, because you can observe this after 2000, there was a prolonged period of, I think, 10 to 15 years, where this increasing trend of temperature was halted, which is known as the global warming hiatus. So, we know that the carbon dioxide and the greenhouse gases emissions are increasing in the current scenario, but still there is some sort of halt. Yeah, so we see that despite having increased greenhouse gases in the atmosphere, we are still having some sort of global warming hiatus. While a lot of literature has addressed different issues which can be responsible for this global warming hiatus, but we can also understand this in terms of the natural climate variability, in addition to the greenhouse gases. So this, for example, if you just look at this and come to this slide, come to this plot. So this I've taken from the presentation by Gerard Mead. So this straight line which you can see is dash curve represents the trend, which is mainly driven by the greenhouse gases emissions. And on this trend, superimpose some natural climate oscillations, which can be anything, maybe which can be any natural climate variability. Suppose if you're lying in this region, so you have obviously you have an increasing temperature driven by this global warming. But there is some sort of negative phase of this natural decadal climate oscillation. So that in turn can suppress the heating which we are seeing this graph. So it is very important to understand the mean state of the climate as well. And also there are some studies which have reported that there are some recent discrepancy between future projections by the symmetric models and the observation. While symmetric models are saying that the Pacific Walker circulation is weakening, recent observation suggests that the sea surface temperature gradient in the tropical Pacific is actually strengthening. That means it is possible these models are not able to account for this multi-layered climate oscillations. Okay, so now we understand that it is important to understand this, natural climate variables. So what are some of the leading mode of well-known decadal climate patterns, which we all know? So on your left is the Pacific decadal oscillation. It is the leading mode of variability in sea surface temperature normally in the North Pacific. It has a time period of around 40 to 60 years. And PDO is defined in the North Pacific, but its pan-Pacific counterpart is called the Interdecadal Pacific Oscillation. And both the PDO and the ISO time series are go-when phase, so they can be used interchangeably. This IPO or PDO kind of structure has in the tropics, you can see an El Nino type of condition. The only difference is that in El Nino, the spatial pattern is mostly confined in tropics, but when you talk about decadal climate, it includes into the subtropical. And also, you can see there is a cooling in the subtropical portions of the other side. So this is in the Pacific Ocean. Similarly, in the Atlantic Ocean, we have something called the Atlantic multi-decadal oscillation, which has a period of around 60 to 80 years. Okay, so these are some leading mode of variability at these time scales in different ocean basins, right? But we understand that from in general, we know that when in our climate science, when we go to larger spatial scales, the temporal scales also increase. Like if you're talking about the decadal time scale variability, it cannot be confined to some ocean basin or some regional scales. So decadal climate variability must have some global signatures. So it cannot be confined just to Atlantic or Pacific Ocean. There must be some global signatures associated with these decadal climate variabilities. So to address those decadal climate features, now we're talking about a study published in journal, which is called Generation of Hyperclimate Modes. And in this work, what they have done is that they have tried to understand the spatial pattern of the multi-decadal climate variability. So first of all, they have taken some observation data set from NISSC from 1817 to 2004. And since they want to address natural climate variability, so they have detrended the data set exponentially.
What is the hyper?
Yes,
Hyper mean then?
sir, it will come. Yeah, so in order to address the natural climate variability, they have detrended the data set to remove the global warming signal. This is a general way to remove the global warming signal. If you detrend the data set. And then in order to remove higher frequency components, they have done the 10-year running mean. Okay. And then they have done the year for the global SST from this observation had SST. So what you observe is a classic what they call as a near global multipole pattern. In the you can see IPO kind of structure in the Pacific Ocean. You also see Indian Ocean following the El Nino, and in the Atlantic also you can see some sort of Atlantic multi-decadal oscillation kind of structure. So these patterns are not confined to a particular basin, but they are global in nature. But since the observation data is just 135 years, so they wanted to increase the degree of freedom. So what they did is that they also did some simulations. So the model which they used was ECAM model. So this model is basically ECAM 5 atmospheric general circulation model, and it is coupled to a single column ocean mix layer. Okay, and also one of these detail is that there is no lateral interaction in this mix layer. So it is all the interaction are going in the vertical direction. So what they did is that they integrated this ECAM model for 2000 years, and similarly they again did they analyzed the output. And they did the year analysis of the global SST. And what they found is a very remarkable similar pattern. So this pattern is not only an observation, but it's also coming out in ECAM model simulations. That essentially, and the pattern correlation is very high, 0.9. So this kind of spatial pattern is what they call as the hyperclimate mode. Why the hyper name they have given is not very clear, but I will come into the later part of this presentation. I will try to address. And also this year one explains almost about 1/3 of the total variance, okay, in both observation as well as in the model. So there are a couple of interesting things in this plot. First of all, this is just a mixed layer model. There is no lateral interaction. However, still you are able to generate this kind of structure in the tropical Pacific, right? So ECAM model can simulate spatial features without any ocean dynamics. Without any ocean dynamics means no lateral interaction, but there are some vertical interaction. So ocean is mixed layer interacting with the atmosphere. So they hypothesize that this global spatial pattern can be forced by some sort of atmospheric teleconnection and feedbacks. And also we see that there is a very strong loading, spatial loading in extratropical regions. Now, this is not seen when you're talking about higher frequency components like El Nino, where you have largest loading present in the equatorial region. Okay, so this pattern is something which they call as the hyperclimate mode, and this is at the multi-decadal time scales. So we'll just go back and we'll try to look at how the spatial patterns look at different time scales, right? So this was the last plot. The last slide I showed something like this, like the multi-decadal time scale and how the plot looks like. But in order to address how the spatial patterns look at different time scales, they have done some analysis, a simple correlation analysis, where what they have done is that they have taken SST in this rectangular box in the North Pacific, and then they have correlated those SST with the global SST. And the data is filtered, like it is filtered to have a frequency of less than 5 years, or time period of less than 5 years. So what they see is that the teleconnection is very regional or local in nature, right? So the SST over this region is correlated with the SST in the surrounding region, not at any other place, which makes sense. Same is the case with North Atlantic also. So you can see that the features are very regional in nature. However, as they go on from annual to decadal to multi-decadal time scales, we see that the spatial features goes on becoming larger and larger for both cases. And towards the end, like at the multi-decadal time scale, we see that irrespective whether you've taken SST in the North Pacific or whether you've taken SST in the North Atlantic, you see a very remarkable similar pattern. So that means that at these time scales, your spatial features are very robust and they are global in nature. And also all this SST has come from this ECAOS simulation, which does not have lateral ocean dynamics. So you don't need lateral interaction to generate these kind of spatial patterns in global sense. I'm not saying that ocean dynamics is not important, because ocean dynamics is important to generate those patterns in regional region. For example, Atlantic multi or decadal oscillation can be is known to be driven by NMR. But how these spatial patterns are connected at global scale does not require that ocean dynamics. Okay, now one more thing which we can see from this plot is that as soon as we go on the multi-decadal time scale, these spatial features become global. Also, we can see that there is some sort of coherence between the two hemispheres, right? So the SST over this region is showing a strong correlation with the SST over the Southern Pacific also. Same is the case with the, not exactly similar, but same is the case with the North Atlantic as well. So that means there is sort of coherence, spatial coherence between the two hemispheres at these time scales. So this is for SST. They've also shown this for the 5 hectopascal geopotential height. So similar thing, they have just taken a 5 hectopascal geopotential height in this rectangular box in the Northern Pacific for 40-year running case, and then they have correlated with the global 5 hectopascal geopotential height. So in this case also you are seeing a global pattern, which is high correlation is global in nature. And there is also, you can see there is some sort of symmetry and some sort of spatial coherence in the Southern Pacific also at around 30 degrees south. Right? So that means that at these time scales, what is happening in the Northern Hemisphere is connected to what is happening in the Southern Hemisphere. And this is further shown by this, what they call as a cross-spectral coherence analysis. So on the x-axis you have frequency, that is 1 by years, and you have some sort of coherence. So what you see is that, so what is cross-spectral coherence analysis? It is just a type of correlation analysis in the frequency domain. So you want to see that how the two time series are correlated at different frequency bands. So what you see is that as you go towards the longer time scale, the coherence starts increasing. So that means as you go towards the multi-decadal time scale, the coherence between the Northern Hemisphere and Southern Hemisphere goes on increasing. So they wanted to see what is the role of the tropics in these spatial coherence. So they did two types of experiment. So in the first experiment, what they did, first is the control run where we have this controls setup. The second case, what they did is that they fixed the tropical Pacific SST to climatology. They did not allow the SST to vary in the tropical Pacific. And the second case, they fixed the entire tropical SST to climatology. And then they run the model for, I think, around 400 years. And then they did the same plot what we have seen in here. We can see. So now what they see is that when they have fixed the tropical Pacific SST to climatology, we do not see any increase in this coherence between two time series for the Northern Hemisphere and Southern Hemisphere as we go towards the longer time scale. There is no preferred time. Right? Here we can see that there is increase, here there is no increase. It is more or less constant plan. So that means that the tropical SST is essential for kind of, it acts as a bridge between these two hemispheres. And same as with this plot also, where the blue line is the control setup. They have done the power spectrum of the 500 hectopascal geopotential height. For the control setup, we can see that there is a increase in the power as we go towards the longer time scale. However, for the fixed SST, the tropical Pacific fixed SST, we don't see any such increase in the power at the lower time scale. So that means that tropical SST are important and they kind of act as a link between these two hemispheres. But why tropical SST is important?
Because they have ENSO.
Which, yeah,
They have ENSO in the control system.
they have not shown the internal, like they've already done it and running mean.
But they didn't
No.
say anything about it.
No. But I feel that ENSO will be there because you can see these patterns. How can they become without ENSO?
But without rocky wave, oceans wave, how do they get ENSO?
Mixed layer is still there, right? Because they have.
Because in that case, ENSO purely doesn't require the propagation of wave.
Yeah.
They do not.
Yeah,
have
yeah,
ENSO
correct.
having.
Actually, what I think is that since they have not shown internal time scale, what they've shown is the multi-data time. So they're filtering the data for TS. And at those time scales, you do not need those complexities. Because studying mean climate is all about studying mean state. And you don't need, even if you take the, instead of this kind of mix this ECAM 5 OZ model, if you take the completely coupled model, what they've seen is that you do not get this kind of spatial pattern which you get in observations. So what is happening, what might be happening in that case is that the ocean model, when you include the complete ocean model into the picture, you might be able to enhance your higher frequency climate variabilities, but it has no impact on the low frequency. Because at the end, you're already filtering the data. Okay, so we know that tropical Pacific is important for this spatial coherence between two hemispheres at multi-degree time scales. Now, one slide on what is the dynamic of this model. So this dynamics of this ECAM model is the simple stochastic model of the anomalies. This is an extension to the Hasselmann stochastic model where they do not have this vertical temperature term. They do some basically I will explain what these terms are. So this T is SST anomalies. It can be also the upper ocean temperature or ocean heat content. So in this case, they have taken the SST anomalies, and this SST anomalies is also damped by this. The damping of this temperature is slightly proportional to this gamma term, and there is also a vertical temperature term which is here. So this is basically this term takes into account the vertical mixing which we have in the mixed layer, and that impact of that on the temperature evolution. And then the last term is the white noise weather forcing that can be the form of winds or maybe heat flux at the surface. Because this whole idea of the Hasselmann stochastic model is that we can have random atmospheric forcings in the form of winds or heat flux, and that is continuously coming in all frequency bands, and that is driving the upper mixed layer, and that mixed layer due to its heat capacity is able to integrate that forcing and giving the variability in a longer time scale. So based on this model, they just try to simulate the model SST with the realistic model parameters. They show simple what they did is that they have plotted the power spectrum of the SST from the model, ECAM OZ model, and also they have plotted the SST from this theoretical model. And this is shown in this blue curve. So what you see is that exactly what you see for this ECAM model, that the spectrum exactly looks like that, where you have increase in the power as you go towards the higher frequency. Low frequency bands, so the high time, longer time, right? So this model is able to capture what we got from the ECAM model also. Actually, the frequency curve is quite similar. So next, what they wanted to address is that what is the contribution of these different terms on the what is the dependence of time scale on these different model parameters which we see. That is, how these different model parameters determine the time scale which we have for this spectrum which we see over this, in this plot. So we have three terms. We have heat capacity, we have damping, and then we have the mixing case, which is highlighted in the screen over the screen. So we just look at the heat capacity, right? So what they've done is that they have many cases, 4 cases. So in the first case, they have taken they have added the mixed layer depth. So basically, if you're going to increase the mixed layer depth, you're going to increase the oceanic memory. Right. So or essentially, you're going to increase the seas. So what they've done is that they've taken initially 50 meter mixed layer depth, and then goes on increasing the mixed layer depth. That is, they are going to increase the they are increasing the heat capacity. And as soon as you increase the heat capacity, first thing is that the variance with the higher frequency starts dropping. You can see that from red, if you compare red and blue. And the other thing is that as you go on increasing the mixed layer depth, you're able to capture the longer time scale variable. This is because the ocean memory is increasing. Now what they do is that they changed this damping term. So there are 3 cases. The blue one is dark blue one is the strongest damping, light blue weakest damping, and this light blue is the strongest damping term. What they find is that as they go on increasing this damping term, the power at the low frequency also goes on decreasing. That makes sense because if you are damping your signal very fast, that is strong damping, then you will not be able to retain the signal, and so you'll not be able to capture the low time frequency benefit. So that was the second case, and the third case is that they have changed the mixing. So this, as we know, that mixing is directly proportional to this term KZ, which is a function of the height of the mixed layer. So what they did is that they took yes, KZ is very large. In that case, your KZ is very large, meaning your mixed layer is very, very deep up to the base of the ocean. In that case, since the mixed layer is very large, what you're happening is that you're able to get a perfect red noise spectrum curve because the ocean is fully mixed. In the other case, what they've done is that they have made this KZ value very, very small. So by reducing the KZ value means you're essentially what you're doing is that you're shallowing the decreasing the height of that mixed layer, and that in turn means that you do not have any mixed layer, and in that case the power spectrum looks completely flat or some sort of white noise because you don't have any mixed layer to integrate that forcing. So what essentially it suggests is that the higher is the mixed layer, the greater will be the greater you will be able to capture the low frequency variability. And this green curve represents the actual realistic case where they have taken some realistic mixed layer depth. And for that case, you see that you see a very realistic power spectrum very close to what the model predicts in blue curve. So this blue and this green curve is very same. So in short, we'll just conclude. So in short, what we can say is that on shorter time scales, we have more sort of variabilities at the regional scale. So shorter time scale, you will have more variabilities at the regional scales. And also at the decadal time scale, what is happening is that there is larger signals in the extratropics. And that extratropical signal continuously force your tropics into form of winds. That is essentially this third term. I would just say one thing, that it's not always the extratropics which drives this third term. This can be some tropical processes also which can drive this third term. But this extratropical pattern can also drive winds over this equatorial region. And that in turn, the equatorial region, what is happening is that it is getting integrated in time because of the mixed layer, which we have in the in the equatorial Pacific. And that in turn, at these time scales, is leading to a spatial coherence at different regions, right? Which we are seeing in the first plot. So this is just a hypothesis which they have given in this paper. So the main point is that at decadal time scales, we should not focus on regional scales. We should be focusing on some global spatial features, which are driven by the atmospheric processes, atmospheric teleconnections coupled to ocean mixed layer. Okay, so we can keep in mind this thing that extratropical forcing can have an impact on tropics. So now we'll talk in the second part, which is much interesting, I guess, because it is related to what is happening in the current 2024 ENSO evolution. So this is something which we have found is called the ENSO transition mode. So what is ETM? I will just quickly go through this because many of you have already seen it many times. So this is if you take the March, April, May average sea level pressure in the southern Pacific Ocean from say around 100. I've shown only from 100, but from 45 to 290 east and entire southern hemisphere. And you do the EF analysis of the March April May average SLP, you will get the second mode, that is EF2. You will get this kind of dipole kind of pattern where your high pressure anomalies in this western Pacific, that is Australia, and in the cold and the negative SLP anomalies in this eastern Pacific region, right? And this spatial pattern is very important because if you just regress the surface wind with this corresponding PC2 time series, you will see that you can see that there is this spatial pattern drives anomalous westerlies in the central and eastern equatorial Pacific Ocean from 180 east to 240. You can see maximum amplitude of the winds, and this is happening in March, April, May. So this kind of winds can have an impact on the evolution of winds from winter to summer, right? So, and also, since this is EF analysis, so we also verified this result by taking the SLP in two boxes, which is highlighted with this SLPW and SLPE. We just took these two boxes, calculated the SLP normally from this individual in these two boxes, and took the difference and called it delta SLP. So on this blue plot is the PC2 time series corresponding to EF2 spatial pattern, and delta SLP is the difference in the SLP in these two boxes, right? So both the two time series are highly correlated. That essentially suggests that there is some sort of multi-decadal seesaw in SLP about the dateline in the southern Pacific Ocean, which is also seen by the far spectrum, significant peak at around 50 years or so. And so next thing is that how this multi-decadal seesaw in SLP about the dateline can have an impact on the ENSO transitions. Right? And this is some, okay, so one slide on that, this ETM signal is also present in the mixed layer, subsurface processes. So this is the degradation of ETM with the 20-degree isotone there and the subsurface temperature of 2 to 50 meters. So we see that during the positive phase of ETM, this negative value means that the thermocline is shallower and we have cold temperature anomalies in this Western Pacific. And so we also have warm temperature anomalies in this Eastern Equatorial Pacific Ocean, right? Interestingly, from TGF to March, April, May, if you look closely, this blue patch becomes darker in this MEM. That is because during MEM, we have anomalous westerlies in the Equatorial Pacific Ocean. And that anomalous westerlies is kind of means easterly trade winds which are there in the Equatorial Pacific are weakened, right? And that weakening of the easterly trade winds is in turn, what it is doing is that in natural, in the climatological sense, we have strong easterly trade winds going in the Equatorial Pacific Ocean. And that in turn drives segment transport to the north and to the south and leads to the upwelling of deep water in the Equatorial Ocean, right? But since now the easterly winds are weak, the meridional currents are not away from the equator, but they are towards the equator. The surface currents, meridional currents. This is latitude. Sorry, that's not very visible. But from 10 north, from 10 south to 10 north. So we see from both the hemispheres, this positive value means that it goes toward the equator, and this negative also means it goes toward the equator. So that means that it is not allowing the upwelling of the cold water during the positive phase of VT. So if the cold water which is there in subsurface is not able to come to the surface, that means your SST will warm. So these are BTM signal is there on the surface as well as subsurface. Okay, now comes to the main part. So how does it impact the seasonal transition of ENSO? So we define a metric delta T, which is the difference in the SST in JJ and EJ. So we have 3.4 SST anomalies in June, July, August, and we also have the SST anomalies in EJ. So we consider time series the difference between two. So as shown by this schematic, winter to summer. And then what we did is that we okay, so we have a time series delta 140 years now from 1880 to 2020. And we also have winter SST anomalies. So what we did is that we divide the all the years based on the winter SST anomalies. So if your 3.4 in winter is greater than 0.5, it is El Nino. If it is somewhere between 0 to 0.5, it is neutral warm, and so on and so forth. We are classified into 4 broad categories, right? And each category is further divided into 2 categories depending upon the phase of the VT. So if you just look at this, you can just neglect all this. Let me just concentrate on this plot. So this means we have El Nino in winter. This also means we have El Nino in winter. But in this case, we have positive ETM forcing coming in the boreal spectrum. That means anomalous westerlies. In this case, we have anomalous easterlies, ETM-related easterlies. Now we see that when we have ETM-related westerlies, we have a larger increase in delta T compared to those winter El Niños when we have negativity. So that means, and that is true for all the cases. In all cases, the positive ETFs will lead to a larger increase in delta T, irrespective of the winter ENSO state. So irrespective of the winter ENSO states, positive ETM leads to a larger increase in delta T. Okay, now only 2 slides. So what is the impact of ETM on different and the transition of ENSO from winter to summer? So let me talk to you about 2014. Now 2014 was a very interesting year because there was a lot of news, a lot of speculation that a big El Nino is coming. There were a lot of news, all the climate models in the world are showing that a big El Nino is about to come 2014. And that is true because if you just look at this plot. So here I have plotted the 3-year running mean of the El Nino 3.4 ST anomalies for 2014 in blue and 1997 in orange. So interestingly, you see in winter, it is exactly same. The El Nino 3.4 ST anomalies for both the years are exactly same. And they evolved quite similarly up to Boreal Spring. But beyond Boreal Spring, 1997 showed a continuous increase in the SST anomalies, whereas in 2014, SST anomalies already even showed a decline before strengthening again in late winter. So based on these conditions, people are speculating that we would have strong El Nino just like because 1997 was a very strong year. So we found that during 1997, ETM value, that is PC2 corresponding to year 2, has a very high value of 1.75. However, in 2014, your ETM value was negative. Negative ETM value means you have unfavorable condition for the increase in delta. And that is shown also by this ETM index, daily index, which I have plotted from March to May, so entire Boreal Spring. So you see that for 1997, where we have this positive ETM value, this ETM index was positive throughout the Boreal Spring. You can see it was positive for the Boreal Spring, and it created a mean condition which favored an increase in temperature. However, in 2014, what we see is that it was negative, it strengthened, then again it started decaying. These are cumulative index. This is not the daily index, it is a cumulative index. And what we can see is that in 2014, the ETM index was negative. It was around minus 0.8 so. So it suggests that in 1997 and 2014, ETM has a contrasting value, and it might have played some crucial role in determining the trajectory of the SST in the equatorial Pacific Ocean. So this is for the current year. So I have plotted the ETM index in bar, which is shown in this blue bar from March 1 to. So you can see that this is March 1 to actually 31st July. Whatever current data I have. So the blue bar is ETM value, the orange is the equatorial Pacific climate wind anomalies, and the black one is the 3.1 SST. So what you see is that ETM was positive throughout Boreal Spring this year, and the corresponding winds, which is shown in this orange curve, are also hovering about. If you plot the mean, it will come out some positive. So the winds, equatorial winds, are also most of the times anomalous westerlies throughout the Boreal Spring, right? So from March 1 to June 19, it was unfavorable to La Nina. So the conditions in the medium did not favor the development of La Nina. However, in recent times, we have seen that the change in the sign, flip of the sign, and ETM anomalies, ETM related AESLP have become negative. That is favoring the winds have also become easterlies. And we can also see that SST, which due to this, maybe due to this positive, become increased and remain positive throughout June, also started showing a decrease. So it is possible that ETM related SLP anomalies in positive anomalies delayed La Nina in current year. And now we can see that La Nina has started forming because ETM is also showing that. In the last slide on the forecast, like how the models are forecasting this Nino 3.5 ST based on different initial conditions. So have taken CFS seasonal forecast from National Weather Service CPC NOAA. So what they on the y-axis you have different initial conditions based on 12 December initial condition, 12 January, February, March, April, May. Okay, and the orange curve represents the 3.4 is 16 anomalies for September, for current September, and the blue one represents for the current July. So what we see is that models based on December initial condition predicted some sort of like El Nino positive anomalies, and it hovered around somewhere around there. But after April, maybe after 12 April or so, the model started showing that the strength of the El Nino for both July and August is weak. That means, and 2014 was a negative heating year. And 2014, after April, the intermittent SLP anomalies started declining. And the models also are showing somewhat similar thing, that after April, the strength of the El Nino is decreased, right? And this is for the current year. In the current year, it is very strong one for 9 months. And the models which were using 12 December initial condition were predicting some La Nina. And the models just before, which were initialized just before the spring, forecasted very strong La Nina in both July and September. However, the latest simulation based, not latest, but based on the May initial conditions, the model showed that the La Nina strength is decreasing. Even in July, there is no La Nina because of the fact that you can see that it is less than -0.5, and ETM is very positive. So it suggests that ETM might be playing some role in determining the course of evolution of these SST anomalies in the NINO 3.4 region and Jupiter. Yeah. That is. Thank you.
Very relevant to this year's Nane actually question.
Yeah, I have checked it. It is not very strong, but we have also seen, because we have also seen that ETM, because it is a decadal time scale, right? So at that time scale, we have some relation with the Indian monsoon moisture convergence and those things.
Anyone else? Okay, thank you.
Yeah.
In the study, what were the initial conditions?
Yeah, so they have not mentioned about the initial condition. What they mentioned is that they have mentioned some specification, like it has a horizontal resolution of 3.75 degrees, and they have not mentioned about the initial condition which I've used to post. Yeah, in the first case, they were control run, and then some experiments they have fixed the climate sensitive to climate change.
Even in the control run, there
Yeah.
was some type that dipole was projected.
Dipole.
I mean that the warming pattern which you were talking about. Yeah, this pattern in control runs.
Yeah, in control itself, because control run has your mixed layer, right? And you have interactive tropic as well. So I think
So climate which year?
I think 1980 to 2010 they have used.
And what is the pattern?
What?
My question is why have not taken included all analysis?
Yeah, so
Any specific reason?
they also so this is the observation had ISST. This is based on the ECAM model, mixed layer model. So very high correlation, spatial correlation. And this is their making Civil 3 models, which is a fully coupled model, right? So there, what they've seen is that in the Atlantic and so you're not getting that amount of spatial covariance. So this study is all about talking about the spatial, global spatial features. So the when you take into account the ocean dynamics, you will be able to generate the regional climate modes like AMOC, which then drives Atlantic multi-decadal oscillation. PDO, those things are essentially have ocean in it. But how those different regions decadal variability is connected, you do not, for that you do not require ocean. You need some sort of atmospheric teleconnection. That is what they are hypothesizing.
It will be online. Thank you. Yeah, so look at situation. The monsoon looks very good so far. Nothing unusual. So just want to remind you that July was 9% above normal. August, only 6 days data we have, 45% above normal. It will change. I'm sure it can be 45, it will go down. There will be a break sometime in the next few weeks. Now, if you look at the all India rainfall on the top, what is remarkable is the number of days the all India rainfall was well above normal, especially here, 15 millimeters per day. I've never seen this before. Okay. So now it's going down. Okay. But look what happened to east and northeast. Okay. They're in very bad shape. They are well below normal. Okay. So more that central India, South India is well above normal, and this is well below normal. I think some models got this idea right in the long-term prediction. Now, how is El Nino doing? It is hovering around 0. Okay. The most recent value is, sorry, this is old one. Next one is, I got right, 0. Almost 0. So it's not yet a La Nina, it's in the neutral phase, but next 1 month it might go to La Nina. Now, I want to compare this particular year with all the other years where we went from El Nino to La Nina. I showed this earlier. I just added a few more months data. This is this year, red one. Okay. So all I can see is at this point, this is closer to 83. Okay. In all the other years, La Nina had already set in July. Okay. Not quite young, but these. These five are in one group and these are another group. So if you want to do any analogy, you have to compare this with 83 or 95, that kind of case. Okay. A little delay in the onset of La Nina. Now, if we look at the weekly data, which is available from Australian Bureau, this is the interesting part. This is the part we saw. It went almost 0 in May, 29 May. In 2 months, it sort of went up and then went down. And May 42 to those waves we saw last time. But it looks like now it's going to start going down. Now, let's look at the July forecast made by various models with actual data. Okay, this is CFSP2, the American version or the Indian one, and I would say they got it right because they predicted below normal in South India, and we had one of the most intense rainfall of all time in coastal Karnataka. Well, matter of fact, I just saw the rainfall in 1 hour. It was 1,000 millimeters above normal. I can't believe it. It is 3,500, 1,000 above normal. So this because the Somali is very strong. It's just bringing moisture regularly to the coastal region. So this feature, this model did not capture. This is okay, comparable to what is there. And it did not quite get the northeast drought feature. A little bit is there, but not very much. This is CFSP2, okay? Now, you look at, this is GFDL. GFDL, I would say, partly got this right. And to extrapolate that with this, I would say it got this right. Okay? So I would say overall, except of course for northernmost India, that part didn't affect. I would say it got this pattern and this pattern. That is GFDL. Let's come to, but the only problem now come to IMD forecast. It is probabilistic, not, you can't compare the two figures. This is in millimeters per day. But still, I would argue that the prediction above normal rainfall here came out right. They gave some hint of below normal here, but they really said below normal here, that's right. Okay. And even this part I'm little intrigued. This little, it happens every year. I don't know what happens here in this part of Andhra Pradesh. And this part seems to show, of course, this is Tamil Nadu, which anyway won't get good rainfall in summer monsoon. But some hint of this is here. Okay? But we can't make comparison because this is not millimeter comparison. But overall, I would say it's quite good. Now, what's the forecast for the next 2 months? Remember that nowadays I'm going to issue the second forecast in the middle of the monsoon. And the forecast says that in August it will be normal, plus or minus 6%, which is, can always do that. You know that you do that, you write 7% of the time. So most of the time they do that, that's okay. Then from September, they're saying 6% above normal. Sorry, not September, August, September. I don't like this. I don't know why they give August and August, September, and give separation. Anyway, I calculated it, I'll tell you the numbers later. So August is normal, means September is well above normal because this is August plus September, okay? So September will be more like 10 to 12% above normal to get this sum to be 6% above normal. And they say their model forecast indicate neutral IOD. So IOD is playing no role. That's their forecast. Maybe right, but IOD is a very tricky phenomenon to predict. I don't think there is any model which gets it right. It develops quite rapidly. It responds to Indian monsoon. I don't think any model can be trusted to do that. Okay, let's what does climate do? Climate says August is 2% below normal. September is plus 10%. So I would say the next to that. Now let's remember climate made a prediction of minus 5% in June to minus 10%. Okay, signed right, number wrong. July, they said plus 5%, it was plus 1%. In both cases, they got the sign right, but number was off. Let's see what happens. Now, let's look at the forecast made by IMD yesterday, or much about it really. Probabilistic forecast for August and there's August plus September is August again. Okay. Now, they are saying that there's some kind of monsoon getting weaker here and partly here. Okay. Now keep this in mind. This seems to be consistent with other models, this part. Okay. And September seems to bring it down. So all the models like September, La Nina would come and rainfall will be high everywhere except Gujarat, and Northeast seems to always go out of place with this. So that's all understandable. Okay, what the prediction from GEFS? This is the American GFS, and this is the European model. I want to notice this part. This is only a 15-day forecast, not the whole month, but it covers most of the month. Today is 7th, 15 days, and we are pretty much end of August. So to me, this is consistent with what I am saying. And this also, this is a little weaker than that. Overall, I would say these two are very similar, except for a minor difference. Okay. So August will probably be normal because of this feature. It will bring down because this is part of the core monsoon zone. Remember that. Now let me go back to my table and show some very interesting features. This year, June rainfall was 147. So I keep comparing with 2016. There was also a El Nino La Nina transition. Okay, there was also 150. Okay? Within that measurement error of IMD, I would say is the same. Look at July. The 304, 306. Amazing, huh? 2 years, I mean, almost same June and July. And I remember 2016 because IMD made a forecast of a flood, plus 10%. For the first time, they became bold after they were successful in 2015. They went ahead and said it will be a flood year. Let's see what happened after that. So the normal year, not a flood year, because August went down. September slightly recovered, but it couldn't do much. Now, the forecast, according to IMD, given on 1st August, they are saying 260 here, that is the normal, and they are predicting 20-30 millimeters more, 185. So we add all this, we get 900, which is better than 860. Okay. And 900 means about 50 millimeters above the present number. Yeah, this is an old norm. I think now the normal value has gone down. So 60 millimeters, 40 millimeters above normal, which is not flat, but it is quite close to 5-6% above normal that many models predicted. But I wanted to look at 83 La Nina, which I showed had a similar 3.4 structure. Again, these were very close. As well, these three are very close. Even the El Nino here, okay. Then we come to July. This was bad, but in 83, because La Nina came up very rapidly, it showed a huge boost in August, which may not happen this year. We don't know. And look at September. Well, September was pretty high, but not as I used to 2019, which was the extreme huge year, but it was pretty high because November 160 is almost 90 millimeters above, okay? And it went to 989. Okay, so remember that 83 was one of the largest flood years in our data set. So the issue is that we are doing better than 83 here. Okay, we are similar to last year and similar to 2016. The question is, will we get 862? Will we get 989? Or it will be? So this looks like many of these. We'll see that. Okay. And if you look at the La Nina development in 2016, it was -4 in May, June, July. And June, July, August to -0.5. So we are not there. We are still at 0. And let's look at some weekly forecasts. I can't show you my favorite 10-day forecast, but they removed it. I don't know why. I don't know why I decided they will not show 10-day forecast. It was my favorite, but it's not there. So this is weekly comparison. Unfortunately, it doesn't agree in terms of exact date, but I would again say that it looks very impressive. All these are correct for the week of 25th to 1st August. This is right, almost, except for the mountain with all this stuff. This is not quite right. This was the forecast. This is not so good. And we are also slightly below now. That's a weekly forecast. I'm talking about the first week. Okay. Now, a few words about Kerala. A lot of talk in the press because of this unbelievable landslide in Wayanad. And actual data, I looked up the Brown website and IMD website. The rainfall there was not extreme, okay? Unless something's wrong with the data. Okay? Because 210 millimeters is nothing in Western Ghats. All of you know that. In Bangalore, we'll be finished. Highest 180 in the last 150 years. Okay, but Kerala should not have. So I'm quite convinced, and Madhav Gadkar pointed out long time back, that is gross misuse of land resources. Mining is going on like hell from the tip of Trivandrum to the top of Maharashtra. Everybody is out of loot anything they can. And so this is happening, okay? But of course, you can always blame climate change and extreme weather. As a matter of fact, what amuses me that every time something like this happens, everybody hides behind what they call cloudburst. I don't know how many of you know the precise definition of cloudburst is 100 millimeters per hour, not per day, per hour. It has never happened in the data except probably in Mumbai in 2005. Maybe for a short period, it was 100 millimeters per hour. But nowhere else has happened. But it's easy to blame so that you escape your responsibilities. So this part, anyway, I would like somebody to look at some of the data because this data from IMD may be biased because unless you have enough rain gauges in the modern regions, you can't get it right because there are large variations. Like it happened in Mumbai, between Kolaba and Santa Cruz, there was huge difference. So that's possible that right at the spot in Wayanad where the landslide occurred, maybe it went along. But when I look at data, so I would like someone to go look up IMERGE, which are great faith in. Whether IMERGE by chance shows in a very small region, 10 by 10 kilometer region of heavy rainfall. If that occurred, then one can always put the claim. Okay. So this is the actual data from the IMD regional website, you can see both the Kerala is below normal and Wayanad is here 14% below normal. Okay, because this is seasonal thing, it's not that particular day. Okay? I saw that day also, it is not much above normal. Okay, now I want to end on this note related to what Shikhar presented. Somehow, not enough people are studying the role of Arctic sea ice loss on the Indian monsoon. Okay, see, Arctic sea ice loss is a huge loss. Whole large areas of Arctic are free of ice, absorbing most solar radiation, altering the SHA pattern. Now, the Chinese have done some work over China, not India. Okay, and they are showing there is a link between sea ice loss and the East Asian monsoon. Of course, it doesn't mean it will affect India. Because look at India, situation is very different from East Asia. East Asia is above Tibet. Okay, so it has much more impact of related to systems. India is protected by Himalayas from there, okay? Not completely. So I'm not sure, but somebody has to look at it. It should be very easy to do. Do a simulation with, I would say, pre-industrial SST with Arctic ice very much there, and let's say the last 10 years, see whether any effect is there. Because only thing with the Arctic sea ice is it covers a large area, it's millions of square kilometers, not a small area, so it may have an impact. Okay, I'll stop here. So next week we'll have an interesting presentation by Bala on geoengineering. We'll start hearing about it more and more, I'm sure. As more and more floods occur, more and more droughts occur, more heat occur, there will be some clamor for geoengineering. So we all better know about it. So next week we'll hear about that. Thank you.